Okay. Good evening, everybody. I hope everyone's having a wonderful day. So before I get started, just as a reminder, remember assignment 2 is out there in the wild. I recommend taking a look at it when you get a chance. And in addition, I did put a summary or discussion video up there right by the assignment description. So do check that out. Give yourself time to make sure you can implement this. Make sure, remember, that the program that you're implementing has to compile. So I've given you a bunch of files that you're going to use with the code you have. Your job is to implement the core aspect of this data structure, of our computer program, the data structure, in this case, a stack that you're implementing using a linked list. And likewise, you're going to be trying to understand how this maze solving program works, the underlying algorithm, so that you could design a couple of mazes that have certain behavior to them. And I'm hoping it'll encourage you to think about worst case behavior when you come across a program and you're like, okay, so what's like the worst this could do? I want you to think about that when you're working on the third part of that assignment. So I'll let you take a look at that and all the best with that. It should be a good time. If you know how to implement a linked list, you most certainly could do assignment 2 just fine. So that brings me to talking about where we were last day, which is somewhat unrelated. The only thing in common is that we talked a little bit about how recursion works, which had that call stack, right? I wanted to come back a little bit to just recursive algorithms, just to kind of touch on a few things and tips and tricks. So just a few things. So remember, when you're designing a recursive algorithm, you make sure you have an appropriate base case, because remember, when we defined a recursive algorithm, the algorithm's defined in terms of solving the problem, but within itself, right? It has a recursive case, but also at some point you're going to get it to where the problem is so small or easy to solve, or you've got the problem to a point where it's going to get to what you want to eventually get to, which is kind of vague for me to say. Like I said, I'm talking about a broad class of algorithms for you. Make sure you define this base case. There can be many base cases. Just like you may have, we seen last day, we talked briefly about Fibonacci numbers. In that case, there's actually technically 2 base cases. So just keep in mind that if you don't have this defined or your algorithm misses the base case, it may not behave the way you intended. In fact, it may not even terminate, for example. Another thing is be wary of the fact, remember, when we talked about how the recursive algorithm actually gets executed on your computer, when it comes to the active memory, remember there's this call stack. So every time I make a function call, it places one of these things called an activation record onto the call stack, right? It gets pushed on there with all the relevant information. And whatever is sitting at the top of the stack, whatever activation record, which is for one of our function calls, whichever one is sitting at the top is what's actively being computed. So that's how we manage function calls and which order they get done in, is that the one that's at the top is the one that's currently being processed. Now here's the thing you have to keep in mind, is remember, each one of these is going to have its own copies of local variables in it. Likewise, so for example, if you have a bunch of variables or even say a more sophisticated set of data that's inside of there, for each one of your recursive calls, keep in mind that if you have many of these, this stack, by the way, on your computer is only of a finite size, right? So you might ask, Dan, do I have to be wary about how much memory I use with this stack? And the answer is yes. So whenever you're making these recursive calls, you may have it just like if you're making many function calls, this stack might grow, or it might be that each one of these activation records is very, very, very fat. Like it takes up a lot of memory. So if you use too much memory on your stack, which remember, this is a part of the active memory while your code is getting executed for your program. If you use too much of this, or it doesn't terminate, meaning that, say, for example, you miss a base case, it can cause a stack overflow. This is when this call stack runs out of memory. Now, in C++, you may run into something like you may run into one of our memory-based errors, Because what will happen is you can almost visualize it like this. Like that this is at some address, and then as soon as you go past this point where the call stack has a cap on it, it may start leaking into another part of the active memory, which you may not necessarily want, and that'll cause something like a seg fault, right? But I must stress that you can manage these types of things if you're careful. For example, in some languages, you'll have what is called a stack overflow exception. That'll be for managing the size of the stack. So these are things to just be wary of, is that if you find yourself having to have what we would call a very deep recursion, meaning that this stack is very, very, very tall, you may want to put into consideration, at least for practical purposes, that maybe you don't necessarily want to have a stack that's going to get that deep, or if you have very fat activation records, meaning, and obviously don't pick on the activation records, please. We want to be nice to all of our friends. If there's a lot of these, this can consume a lot of memory. So this is a practical consideration I want you to have when you think about this. Like I said before, if you have many of the recursive algorithms that we've seen, there's actually ways to implement those using loops, for example. There's iterative solutions for these. So just take this into consideration when like which one makes a little bit more sense to do. So likewise, like I mentioned, you want to make sure that when you're recursively defining how you're going to solve the problem, always ensure it's reducing the problem size when you recursively apply your solution to it, your algorithm. Likewise, make sure it advances your computation. You don't want it where it just keeps calling on the exact same problem instance and doesn't actually advance the computation at all. Otherwise, it may not terminate. Now, two things I wanted to point out, these are more pro and con points I want to touch upon, is that compilers are exceptionally good at optimizing recursively written code. Some programming languages are actually modeled all the way around with recursion. So just be aware that even though there's some of these pros and cons that I brought up, for example, being considerate of how much memory you use, keep in mind that compilers are often designed to optimize recursively written code. So even if you're saying, okay, I can either use the recursive algorithm or an iterative one that uses iteration, keep in mind that this compiler might be able to optimize it in a way that's still going to do fairly well without having any consideration of extra work that you need to do on your side. One big advantage of recursive algorithms is very often they lead to very, very simple ways of describing algorithms. Sometimes it's almost to the point where it's just like, like you might look at it and say, that's it? That's really it? And that's often how it might play out. So sometimes if you try to translate these into iterative solutions, like using loops, for example, it may not come out as pretty as you'd hoped it would have. So sometimes those are a little bit more complicated to come by. But keep in mind that you can do it. The easy way you could see this is conceivably speaking. Remember, with recursion, I use this call stack. The ultimate way to simulate a recursive algorithm is you just make your own stack and you just manage it yourself, right? But remember, this call stack is related to the system. So if you can take advantage of the system stack memory here, wonderful, because this stuff is going to be nice and close to what we're dealing with when it comes to memory. And we want to make sure that those memory accesses, if they're really close to what we're dealing with the lower side of our memory addresses, or for example, memory that's easy to access, this stuff is often handy to get to much quicker. So just keep that in mind. One other detail. Remember, like every time you call one of these functions, it's going to introduce space that's getting used, right, for each one of the activation records. So take that into consideration. It may use extra space, but like I said, you can typically rewrite these using loops. So for example, we've seen the example last day where I was summing over numbers 1 through n, and I showed you a way I could do it with a for loop, and then I showed you a recursive way of doing it. Many, many algorithms of that kind are very easy to transform between a loop and recursion. They have often special names for them, but I'm not going to go into those details here. But like I said, one drawback is that you may have, if you have a lot of information going on with that call stack, that's something of a practical consideration you need to make. But like I said, recursively writing and solving problems it's a very beautiful thing if you get it working right. But yeah, no. One thing I do want to point out before I proceed to the next thing we're going to discuss, other than if you have any questions, is that I did put actually another example. It's going to be in the notes after class. If you wanted to see how, for example, when I counted my friends here, when I had my friends and I was counting them, suppose I wanted to sum over an array, for example, recursively. I give an example for how you might do this. So if you want to take a look at that, just take a look in the notes. It's going to be sitting there right after this discussion here. So are there any questions about what I've mentioned here? So I just wanted to give you some tips and kind of notes to be considerate of when it comes to recursion here. We're going to see lots of examples of recursion in this class. So just be aware of that. So this isn't going to be like the end of our discussion about recursion. We're going to see lots of examples of recursion. It's a very useful, it's not only a way of writing and solving problems, and like a tool we can use to describe them, we can actually implement these on actual computers. So it's not like they're just some weird abstract thing. They're a very real way of describing how to solve problems. So if we're okay with that, give me 2 thumbs up. Sure. Okay. Sure. So just to clarify, what's happening in your case is that, say for example, like this is just for hypothetical purposes, like say this is the main function and it calls some function. I don't know, this is like some sort of function called do something. So when that occurs, so when you you require the computation of do something, that's what the computer is going to switch to processing because it's on the top of the stack. Now, when this activation record is made, it has all the local variables associated with your function call. So those are things that the compiler can determine, and it'll be able to set aside when it comes to the memory that's going to be associated with this activation record. So when you make a function call, it's no different than what we've talked about here. The only difference between, say, recursion, more as this idea, and just any old function call is just that we're calling functions that are of the same name and signatures over and over again, potentially, but often with different inputs. So remember, this call stack it's no different. It's no different than, so when we talk about function calls, the call stack is the exact same mechanism that's being used whenever you call a function. So if you call one function, all it happens is you get an activation record placed at the top by pushing it onto the top of this call stack, and it will perform the computations for whatever is on the top of the stack at that time. Does that answer your question? No worries, yeah, just remember that the call stack, this is an important part of what's actively being processed with your computer program. It's not specific to recursion, but it's an important mechanism to understand when you want to think about, okay, so what exactly is the computer doing when it carries out this recursive algorithm when I implement on the computer? So if you ever find yourself working with some recursion and you're just not sure what it's doing, just take a look at what's happening. Look at the recursive call, so whichever one is occurring. So for example, if you have, say, 2 recursive calls happening, well, the first one always is the one that gets executed, right? So you know that that's going to have an activation record that's going to be placed on this call stack, and you won't be able to proceed to the second call until the first one's done. So if you ever find yourself just unsure what's happening, just go back, draw a picture of a call stack, and see what's happening with it. Okay? So that brings me, so I talked briefly about that one example you'll find in the notes. This one actually has code, so just be aware of that. I like to make sure you see some code and some abstract stuff. So whether it be pseudocode or actual code, I want to make sure you see a bit of both here or there. So anyways, I want to talk about an example of a recursive algorithm. And I know you've probably seen this algorithm before. So the great thing is I don't have to go into much detail about it, except for just what it looks like when I write it using recursion. So I know you've probably seen this guy before. Binary search. So you may have heard of this interesting algorithm. So what we're going to do is we're going to consider the search problem where I'm given an array L. And I'm going to suppose that it's n integers just to keep it simple. And I'm going to have a key or value x. And I'm going to assume that array L is sorted. So this is a special assumption I'm making. So when you think about this, this isn't just the search problem like I had before. What was the algorithm I had to use for the more broader case of the search problem? What was that algorithm again? We talked about it. So say, for example, the array isn't sorted. Which algorithm would we use? Or which one we could use? Linear search, yeah, very good. Now, what if I told you, and now if you take a class like CS 340 with me, you'll actually learn that linear search, when the array, for example, is completely, like you have no information about what the input array looks like, linear search is the best you're going to be able to do. So you might ask, okay, so, oops, linear time just seems to be something we'll have to deal with, because the easy way I can argue it for you is suppose that you don't know if x is in the array or not. Well, you'll have to check all the elements in the array first, right? So just keep that in mind. But now I want to put in this new assumption where the array is sorted. And we can do much better in this case. So let's talk about binary search. Now, for those that have seen the iterative version of this, say, for example, in 115, binary search does not necessarily look like this if you use iteration. Instead, you'll have a while loop. But you'll notice that if somebody that's ever, how many of you have seen binary search before? I just like to take a little poll, see how many people have seen it before. I know that there's some of you that have, yes. So you might look at this and say, Dan, that's really all it is? because this is a lot shorter looking, right? It's like a lot nice and shorter, right? So what? Just to remind you, remember the setup for this version of the search problem is that all of my elements are sorted, just like I have my friends here. So I have them sorted by their height. And yes, I added in metallic Simba. Yes, this is Simba spray painted with metallic paint. It's just, I thought it was awesome. So anyways, notice here that all my friends are ordered so that their heights are from smallest to largest. This guy could be number one. This guy could be number one. I don't know. Either way, we're just ordering them from height. Now, you could, as long as you could do this with all of your elements, you could use binary search. So it doesn't necessarily have to be that they're integers even. For example, strings, you can have measurements for how you're going to order them. We call these, for example, comparable elements. So keep in mind that binary search can be applied in those settings as well. Just like linear search can be used when you have just comparable elements, right? You know which one comes before another one, just like how I can list my friends from shortest to tallest. So I could tell you, based on examining them, I could tell you which friend comes before the other with respect to height. So I could do this with integers because they just have magnitudes, right? So anyways, let's talk about binary search. Now, the first thing you'll notice right away, based on how I've described the search problem to you, you'll notice that my input parameters are actually a little different. Does everybody notice that? Notice that instead of having just two, like one or two, depending on what you'd prefer, I don't just have the array. Actually, sorry, I would have two at least. So notice that I have an array, I have the key, but I also have these two other values. I have L and U. So this is actually going to be how I'm going to recursively define binary search. Now, if you're familiar with binary search, often they refer to it as a lower limit and an upper limit, or a lower bound and upper bound. And the whole idea is that if I know that my friends are, for example, just say my friends here, they're ordered from their heights, right? So I don't have to necessarily scan them from left to right. Instead, I can actually make break with a lovely way of doing this through a guessing game. And that's actually how binary search is going to operate. It's very much like a guessing game. So for example, instead of having to start over here, what I could do is I could start, say, somewhere in the middle. So I perform some guess in the middle. And here's the neat part about this. Whenever I say this is my middle element here, all of the, so I put my middle element out a little bit further ahead. Notice that all of my friends to the right of my lovely friend here, all of them are taller than my friend. All the ones to my left of my friend right here are all smaller than my friend. Sorry, they're shorter. They're not smaller necessarily. They're shorter. So what I could do, so here's the idea. Here's an idea for you. So suppose that I was looking, for example, for my non-metallic lion friend. Suppose I'm looking for my non-metallic lion friend here. Now, I want to know whether my friend here exists or not in my list of friends. Well, what I could do now, because I know that my non-metallic lion friend is shorter than the current friend, I know that it has to be over here, right? It can't be over here with my green friend, for example, or this lovely cowboy. So what we could do is we can recursively examine now a new range of elements in the array, so I can narrow what we would call the interval of elements that I need to look at, dictated by the lower bound or lower limit and the upper limit or upper bound. So, for example, here, all I have to do is examine now this part of what this would tantamount to my array. So I only have to look at these two. So what I would do is I would try to find a middle position. I would figure out what that is, and then I can examine if the current one is my non-metallic lion friend. And if it is, then I could say, hey, look, I found it's in this position. Otherwise, I could apply this process over and over and over again. So in fact, you could play this kind of guessing game with somebody by just, so for example, if you may have played this game before, where somebody asks you to guess a number, and you ask, oh, is it too big, or like, is it larger or smaller? So numbers have this nice property that you can order them like this. So it's very much the same idea. If you use that strategy, the one I've described here, always by picking in the middle of what the range could be, and if ever it's not what it's equal to, you could examine the left half or the right half. So if you do this over and over again, you could whittle this down. In fact, this algorithm I described to you is actually the best you're going to probably do without any more information. Actually, technically, it is the best you could do in this kind of circumstance. So let me walk you through the pseudocode here. So I have an array. I'm given X, I'm given L, and I'm given U. And the same output as before for the search problem. I'll address those two extra parameters and what we do with those in a moment. So we're going to have it where I want to know whether our case where the lower and upper limits are going to cross or not. This is when L is greater than U. So for example, if I keep doing this process, say for example, I was looking for this guy. And suppose I only had these 4 friends. So if I were to do this process over and over again, so I might pick this one, and then I go to my left, because this isn't the friend I was looking for. If I were to look at this and okay, so I'm going to examine, well, my lion friend is taller than this metallic Simba. So I know that it has to be somewhere right here. But when you actually carry out the halving process, what you end up having when you update L and U, they're going to cross. Their intervals are going to cross. This is what this case is. And this is, in fact, going to be when you return -1. What if the range is even? Which middle element should we choose? So I'm going to address that in one moment. So now if the intervals don't cross, meaning that the range you have currently has at least one element that you could examine in it. So if there's currently L and U such that there exists at least one element, then you go to this else block here. In fact, I think let's close off that. So what I'm going to do is I make the guess in the middle. So the way I compute that is I take L plus U divided by 2, and then I round down that number. So notice that I'm using the floor function here. So remember the floor function, if I gave you something like 4.6, the floor of 4.6 would be 4. It rounds down, it chops off the fractional part. And you may be familiar with this because if you use integer types and you perform division, this is very much what it does. It automatically, it's operating like floor does. Because there's never a part where you're dealing with the fractional component, right? When you divide two integers with primitive types of type int, right? So if you're actually implementing this, you would not need to call like a floor function here. You can actually just straight up just do L plus U divided by 2 if you're just using type int, for example. So keep in mind, take into consideration the language you're working in whenever you're dealing with little things like this. So now, like I said, I examine my guess, what is now the middle position of what I'm examining. If it in fact equals the key or value, then I just return that position. I'm done. I found it. Otherwise, you have two possibilities that can happen. There's only two possibilities because the array is sorted. So either X has to be in one half of this, or it's in the other half of it. So in one case, if for example, L sub mid is less than X, so my guess is too small. It's too small, it's less than the key. Then that means that I need to consider the right half. So I have to examine, say for example, in this case it would be that I examined my friends over here. If say for example I'm looking for this lovely jolly green character here. Otherwise, I examine the left half. So that's, believe it or not, all there is to binary search when you describe it recursively like this. Are there any questions about binary search? So I must stress that I do have a full working example in the notes, and I also will give you the code for this as well. So just keep in mind that if you want to play around with this, I will be giving you the code for this after class. So if you find yourself just wanting to say, hey, look, I want to see what this thing does, I will include the source code in the notes. So the point I'm getting at is that this is binary search, and I want to now analyze it. So the big point I want to get to is analyzing a recursive algorithm. So first, I wanted to illustrate that binary search can be written quite simply, just like this, but also I can use the description of it recursively to analyze its running time, which at first it may not be very clear if you were to use an iterative approach to describe binary search. So are there any questions before I proceed? So we're going to try analyzing the running time of binary search. Sorry, I'm moving my threads up so I don't knock them over like last time. Okay, so let's head over here. Let's head over here. Let's do worst case analysis for binary search. Actually, let's stop it right about here. So I'm right about over here, somewhere about here. Because I want to have the sum of the pseudocode here to make it a little easier for us to analyze. So we're going to be adopting the same ideas we've done before, except we just have a little wrinkle to this because we have this recursion. So the first thing that we might have to consider is when we're doing worst case analysis, we have to identify a worst case scenario, right? So are there any suggestions on what the worst case scenario will be for binary search? Any suggestions at all? I'll give you a hint. It's nothing too surprising. Yeah, when the key is not there. Perfect. So the max number of recursive calls Oh no, I lost my little turtle friend. Recursive calls occur when X is not in L. Perfect. Perfect. So now we got to determine the time complexity, right? We got to count operations like we were doing before. But now we have recursion here. Now, believe it or not, the game plan that we're going to use is actually really not that much different. So that's the good news I have for you. So at first, what we're going to do, so I want to make sure that I'm very clear about the analysis for the recursive algorithms that we typically will run into, is I'm going to give you a little bit of a tip here before I proceed. A tip. Ignore the recursive calls first. Count all the non-recursive steps or work. I'll put in quotation marks. So what we're going to do is, that's the first thing we need to do, is we're going to ignore the recursion. We're going to analyze this algorithm without considering the recursion. We're just going to treat those recursive calls just like if they were a constant operation. So we're going to do that first, but then we want to bring in the recursion again. That's where we're going to formulate what was going to be referred to as a recurrence relation, which is going to represent our complexity function. But keep in mind that we have to take into consideration a couple of things. How many recursive calls are happening and how big or how large the pieces are of what we're trying to solve for that recursive call, if any. So let's head back over here. Let's look at our pseudocode here. So I'll have a much more lengthy explanation of how I'm going to count these first in the notes, but I'm just going to draw it out just like we've done previously, so you can just see the exact same idea as I had before. So the first thing is I would like to identify constant numbers of operations, just like I did before. So remember, this isn't going to be much different. Oh yeah, I pulled out one of my favorite markers. This one smells just like cherries. It's a scented one. Just like, don't do this with a normal whiteboard marker. Ah, it smells like cherries. I'm not even kidding. I've had this marker for, I'd say, like 7 years or something like that, and it still works. It's actually quite amazing. I haven't had whiteboard markers that have lasted that long ever. It's actually kind of weird. So if I'm trying to count these, well, I'm just going to do what I did before, right? So notice that I have all of this inside of here, and I have this if statement. What I'm going to do is I'm just going to count all of these up. Notice that an if statement where I check this comparison and return -1, that's some constant number of operations, right? So that's one part I can identify. And the other part's all of this else block, right? So I have these two right here. So this first block over here, say the if statement here, takes some C1 many operations. All of this here, if I ignore the recursion first, so just remember, the first thing I'm doing is I'm ignoring the recursion. So I'm just going to treat them like there's some simple operation, which, remember, recursion is just I'm still calling functions anyways, and you know right away that this is a subroutine, right? Even though it's defined in terms of itself, right? It's still a subroutine, so you know that's not an elementary or primitive operation, right? It's not simple. So we're going to count this all as some constant number of operations. However, with the big caveat that we have to know what to do with these two cases here. These are going to be the ones that we're really going to have to play around with a little bit. Now I must stress, just to remind you, that if I have C1 and C2, what are each of these in terms of big O? So if I have C1 and C2, remember these are a constant number of operations, what is that in terms of big O? It's big O of 1, perfect. So just remember that C1 and C2, they're big O of 1, both of them. So it really does not make much of a difference if you just wanted to write out C1 and C2 in your complexity function, or if you literally just wanted to replace them as a 1, for example. From a big O standpoint, it's going to be no different, which is kind of interesting in its own right. So that's something I want you to convince yourself of, that you can actually always do this. So now this brings us to another point. When we look at our algorithm here, if I'm going to examine this and I evaluate this function, how many times can I perform a recursive call for just one call of this function? How many times? Now I will warn you in advance. It looks like there's 2 here, but how many are actually happening? There's only 1, right? Either it's going to do the else if block here, or it's going to go else if it doesn't actually find it. So keep that in mind when we do our analysis. There's only at most one recursive call that's going to happen for each one of the calls of binary search. So before I proceed, I haven't really told you what I should be setting these initial parameters as, so let me address that. So let's talk a little bit about that. So you might ask, Dan, what should L and U be when I start this process? Well, this, I feel like I need to acknowledge this. So when you initially set this, you're going to set L to be 0, and U is always going to be set to n minus 1, where n is the length of the array. It's the number of integers in our array. So you might ask, Dan, how exactly do you make it look like L, like the array L with a key X? You could create something called a driver method or a driver function. What you do is you just simply write the exact same algorithm. So you write algorithm binary search, you have L and X, and then you make a call this, where L and U are set to 0 and n minus 1, respectively. That's why we call it a driver method. It's like bootstrapping or starting up the recursive algorithm. So if you find yourself looking at this like, okay, so that isn't an array with the key X, that has these extra parameters. If you ever find yourself wanting to write it like that, there's such a thing as called a driver function. I'll have some remarks about that in my example that's in the notes. If you want to look at the C++ example I have there, I show you what one of these would look like. It's really simple. It's really simple. It's nothing too special. It's just a simple way of writing out this so you don't have to have these extra parameters whenever you call binary search. Okay? So we have it where we know what's going to go on with this. So remember, there's going to be one function, so one recursive call is going to happen for any one call. For one call, is going to be one recursive call at most. Each time, it's performing some constant number of operations. So just keep that in mind when we do our analysis here. Yeah, well, keep in mind, regardless of if say, for example, it does in fact find X, or if it doesn't find X, it does that comparison, or like say if it has to examine the left half or the right half. Notice that in either one of those two, any of these cases, if I ignore the recursion, I treat the function call just like it is a single, it's just some simple operation. It doesn't matter which one actually gets called. All of them, if you ignore the recursion, all of these things, even if you added them all up, is still some constant number of operations. So we haven't quite yet addressed the recursion part yet. Yes. Yeah, so keep in mind that I have not yet dealt with the recursion yet. All I know is that it happens at most once for each function call. That's all I know. So let's do this. So the recursive step makes one recursive call. One recursive call where the number of elements U minus L is halved. Now I'm going to put that in quotation marks. So I mean halved. So remember, just keep this picture in your mind when I'm doing this. So imagine I have the array. Suppose that this is the range I'm looking at. Say it's L and U. So I have L and U here. Actually, let me add one more element to keep this a little easier for us to see. So when I check if our guess, the middle position, is X, I don't have to look at this one anymore. So if the left recursive call happens, it's going to evaluate it on this, right? And if the right half is examined, it calls binary search on this, right? Now, you might ask, Dan, depending on the parity of the length of this interval, this might not be the case where each one will have an equal size, right? For example, when I had the case where it was one less element, you'll notice that my guess will always be like one off from what would be the middle, but the middle, there's like a true middle doesn't actually exist for the middle element. I have to round it down. So in those cases, you'll end up where one side has a little bit less than the other. I'm going to make a simplifying assumption that will bound this running time regardless. So here is what I'm going to do. So each is halved. So now, we will make a simplifying assumption. So this is the assumption I'm going to make. And I must stress, I can make this assumption because it will bound from above the running time of the algorithm. That's why I'm allowed to do this. If I didn't, like if I wanted to exactly calculate out these halves, regardless, I can also do that. It's just that the analysis gets a lot trickier to do. And I don't want to burden you with that. The assumption that both halves, the ones I'm referring to in that picture, both halves have the same size. N minus 1 over 2. Now you might ask, where does n minus 1 over 2 come from? So you imagine that, suppose that the number of elements is how many are in the interval. Remember, n in the original declaration of the algorithm will be the whole length of the array, but as we proceed in this algorithm, u and l will govern how many elements we're actually looking at. So if suppose that this is n, you don't consider this one, right? So now you have n minus 1 elements, and you're halving this, that's where it comes from. So notice that if I'm assuming that they're of equal sizes, then this is where it comes from. But it is an upper bound on how many elements can be sitting in one of the two halves. So you know that any one of these two halves can't exceed this number. Okay. So that's an assumption I'm going to make. It just makes our analysis a little bit easier to play through. There's some other properties I could use, but I want to save you some time here. So now I'm going to define a complexity function. Let t of n be our complexity function. Putting all this together, so remember I talked about the constants when I was ignoring the recursion. So putting all this together, we have recurrence relation. Now, if you've never heard of a recurrence relation before, all it is just for our purposes, a function that is defined in terms of itself, which is quite interesting given that we are talking about a recursive algorithm, so it kind of makes sense that the running time can also be defined recursively. So it would be t of n is equal to t of n minus 1 over 2 plus 1 if n is greater than 0. And t of 0 is going to be equal to 1. Now you might ask, why do we have t of 0 and why isn't this t of 1? It's because if you look at the algorithm, you might ask, okay, so like, when do we stop? It's when those intervals, the L and U, they cross over. But what does that mean? There's no elements to examine anymore. That's when this algorithm will return -1 for a recursive call. So that's why we have t of 0 is 1. But remember, I'm just going to be formulating the size of one of these intervals I'm going to be examining. So when I'm given one of these of length n, I'm either going to have n minus 1 over 2 in this side or n minus 1 over 2 in that side. So I want to examine what's going to happen with my recursive call here. So remember, this is like our representing the running time for the recursive case. And this is all of that non-recursive work. Remember I had C1 and C2? If you really wanted to, you could put C1 plus C2 right here. But I'll just put 1 there because remember C1 plus C2 is big O of 1. It keeps things a little easier to write down. So anyways, are there any questions about where this came from? Just to be very clear. So if it helps at all, remember, this is representing the total amount of work that's happening non-recursively. So this is all the work that happens when I ignore the recursion for one of the recursive calls. Sorry, one of our function calls. And this is representing the problem when I apply the recursive call, right? So this is all the recursive work. This is all the non-recursive work. But remember, this algorithm will continue to execute until we get down from the recursive case down to our base case, whether it be it finds the target or it fails to find the target. In the worst case, it's going to hit when these intervals cross and return -1 because that's our worst case scenario. So are there any questions before I proceed to try to solve this? It looks a little bit daunting, but I assure you it's actually not too bad. Yes. So this is now just to be very clear, this is the base case for our recurrence relation, but this is actually representing, just to come back over here, let me just move over here, just to kind of tell you where these two pieces are. Because remember, we're measuring the worst case time complexity and we're looking at the worst case scenario. The worst case scenario is when I have these two intervals cross. It's when this if statement up here is going to happen and it succeeds. So this is when t of 0 is going to happen. It's when I have no more elements to examine, which is kind of a little different than what you'd expect. So this is our case when I have t of 0 occurring because this is when the algorithm is going to be successful, when it has no more elements to examine. Otherwise, it's going to perform one of these two recursive calls. And each of those has a size for how many elements you're going to have to examine. And that is actually going to be bounded by n minus 1 over 2. Does that clarify your question? Hey, no worries, no worries. No, I always have to make sure I'm clear about these things. No, thank you for asking. Okay. Now I'm going to show you a technique for solving such recurrence relations. Now you might ask, Dan, what does it mean to solve a recurrence relation? So what you're going to do is, so the idea of solving a recurrence relation is to come up with a simple expression that represents this without any of the recursion. And then once I have it in that form, then I can tell you what the big O looks like. So that's what I mean by solving it, is I'm going to just give you a simple expression for t that doesn't actually have any recursion in it. So anyways, let's proceed. I'm going to use what is called repeated substitution. So I'm going to show you this technique. It's really handy. In a course like CS340, I would show you even more techniques for dealing with these. So let us solve t of n by repeated. Sometimes people call this iterative substitution. I'll just call it repeated substitution. But if anybody ever tells you, oh, iterative substitution, it's the exact same thing. So what does this mean? What does it mean? What we're going to do is we're going to try to find a pattern by expanding the recursive part of our occurrence relation. We're going to try to expand this part by substituting in what its input is and try to find a pattern. So we're going to try to find a pattern. And we're going to do this until we reach the base case. So you might ask, what does that look like? Now, if you ever find yourself curious about checking these, now, in this class, I can't make any assumptions of your background when it comes to mathematical induction. But if you knew mathematical induction, you can actually use your guess. You could verify your guess using something called mathematical induction. But I'm not going to focus on that in this course. So anyways, let's try doing this, okay? So we're going to try to find a pattern for T of n. And once we have a good guess, I might be able to find a pattern, and that might help me express the complexity function without any of this recursion business. So I end up with a simpler expression based on just n, none of this recursive part. So let's proceed. So what I'm going to do is I'm going to expand the recursive part by writing a new equation. So that's what I'm going to do over and over again. And we're going to try to see if we can find a pattern, okay? So I have T of n. Remember this, we have T of n is equal to T of n minus 1 over 2 plus 1, right? Now I'm going to take this and I'm going to see what it means when I substitute in this right here. So I'm going to take this and I'm going to now apply whatever that definition is to see if I can get a pattern. So now I'm going to consider this right here. So I'm going to put that right here. So I'm going to have T of n minus 1 over 2. So I'm going to try to find a pattern. Now, do you remember my discussion about bananas the other day? How I had a banana and I said, oh, it's a banana minus 1 and so on? Well, remember, T of n, if I define it like this, so this whole thing that I have here is a banana. So now I'm substituting in a banana. And now I'm going to have to apply the definition of the recursive case, which is banana minus 1 over 2. But what's banana? Banana is n minus 1 over 2, right? And obviously I need my plus 1. Now let's simplify this a little bit further. Now, if you play around with this numerator of my overall fraction here, you end up with something that looks like this. N minus 1 minus 2 over 2 squared. 2 squared plus 1. Now, you might look at this and say, okay, Dan, what exactly is going on? So let me write out, I'm going to write this out in a little bit more of a suggestive way, just to give you an idea what's maybe going on. I'm going to write out another term once I have this pattern. So if I simplify this down, now keep in mind, if you're not convinced by my pattern seeking abilities, you can always just substitute in now whatever I have there into this just the same way I just did here and see if the pattern continues. So I would have n minus, so notice that 1 is 2 to the power of 0. 2 is just 2 to the power of 1. And I have 2 squared in the bottom, plus 1. Now you might ask, Dan, where'd you get that from? It's all intuition at this stage. I could always formally check this using some more advanced tools. But yeah, you try to seek out a pattern. And if you keep applying this over and over again, you'll end up with something looks a little bit more interesting. So what I'm going to do is I'm going to now substitute this in and see what we get. So I'm going to have n minus 2 to the power 0 minus 2 to the power 1 all over 2 squared. So I'm just going to take this. I'm going to see what this is. Well, remember, all of this is a banana. Remember, this is all a banana. So now I need to put that into the recursive case. This looks a little bit daunting looking, but I assure you the pattern's actually quite natural. So it'll end up being, if I simplify this out, I'm just saving us some time here. It'll be n minus 2 to the power 0 minus 2 to the 1 minus 2 squared over, instead of j plus 2, I haven't quite got there yet. I want to figure out a pattern here. Sorry, let me just move this arrow here a little bit. 2 to the 0, 2 to the 1, and 2 squared, all over 2 cubed, plus 1. Now, I can keep doing this over and over again, simplifying it down, but you'll notice every single time I do this, I increase the number of powers of 2 I have on the top, and every time the exponent here goes up by 1. In fact, it's technically going up, yeah, it goes up by 1. So if you keep substituting this in over and over again, you're going to get a pattern that's going to arise from doing this if you keep applying this over and over again. So if you keep substituting, creating a new equation for each of these, you'll end up with n minus 2 to the power 0 minus 2 to the 1 all the way up to 2 to the j. So we're going to try and keep applying this over and over again until we hit the base case. But if I tell you that this exponent's j, what should the exponent be in the denominator for the 2? Yeah, it's 1 higher, exactly. It's going to be 2 to the power of j plus 1. Now, if I substitute this one in, so you do this several upon several times, I end up with 2 to the power 1, sorry, n minus 2 to the power 0 minus 2 to the power 1, all the way up to power of j plus 1, because it goes always up by 1 here. And then the denominator always is 1 higher than this. So it's 2 to the power j plus 2. This is all plus 1. Now, like I said, this looks a little complicated, but I assure you it's not. Once you see this pattern, I will ask you to convince yourself of this pattern. Every time you substitute in the recursive part, see if you can expand it and see if you see this pattern arising with the powers of 2. This is actually quite intuitive if you actually think about it, because every time I discard a half, but the halves aren't like always the same size, right? They always grow, sorry, they always shrink, but they're always getting halved in their size, right? So that's why you'll see that the denominator of this is always a little bit bigger than the largest exponent I have over on the largest term. So anyways, you might ask, okay, so when do we stop this process? We stop it when we have t of 0, right? So that's when it's going to stop. The input value given to t on the left-hand side decreases with each new equation. With each new equation. That's how you know it's going to eventually have to go. It's going to keep dropping in its value, right? So you know that at some point it's going to hit when we reach t of 0, right? We stop this process, as in keep rewriting all these equations out until we hit when the input of this is equal to 0. This process, when we reach t of 0, now let me tell you exactly when that is. So I have an idea of this pattern here. So let me write out when exactly this is going to occur. So let's head over here. Because now I have some idea of what's going on with the input of this function every time, this recurrence relation. So notice that I'm now talking about the complexity function. Notice I'm not saying anything about the algorithm anymore. I'm talking about the complexity function. So let's talk about effectively what's the stopping condition of this recurrence relation. So we stop this when n minus 2 to the power of 0 minus 2 to the 1 all the way up to 2 to the j plus 1 all over 2 to the power of j plus 2. Remember, this is the last right-hand side I showed you over here. That's the final one I showed you, because when that recursive call happens, you're going to hit the base case. That's the intuition behind it. We want when this happens. Like I said, this looks a little daunting, but it's actually not that bad once I show you how we're going to unravel this pattern. So I'm going to take all these things I just wrote over there. I'm going to write it out like I'm spreading an accordion. So watch this. Then t of n is going to be equal to 1 plus 1. Each of these is for the non-recursive work. Each of these. 1 plus 1 plus all the way up. There's going to be a bunch of 1s I'm adding. Then we're going to have it when we have this final call that happens. 2 to the power of j plus 1 all over 2 to the j plus 2 plus 1. Now this is where we have to be a little bit careful about how we're counting things, okay? So you notice how many equations I was writing up on the board over there? Notice that I had, every time I write out a new equation, the exponent on it, the j term, always would go up by 1 every time I had substituted in a new equation, right? So I'm going to use this value j that I have. I'm going to use this to figure out what's going on with respect to n. That's going to be my end goal here. So when I do this, I'm going to have a whole bunch of 1s. So remember, I want to know when that base case is going to occur. So I want when this is equal to 0. Because this is our final invocation of the recurrence relation. And that's when I can truly compute what the value is. But here's the neat thing. If you count up how many equations I was writing out. So I'm going to take this 1 out here, and I'm just going to throw it in with this bunch. I want to kind of walk ourselves over here, just briefly. I want you to look at the left-hand side I have over here. Just look at the left-hand side. You don't have to worry about anything else that's happening over here. So this is the part where I'm referring to it. I like to think of it like I'm spreading an accordion here. So notice that when I substitute it in here, I have it where this is going to be, originally this is n minus 1 over 2. I place this here. Notice that the exponent here, that's 1. This is 2. If I did this again, it would be 3. If I did it again, it's 4. And so on, and so on, and so on, and so on. So, you might ask how many equations I have if I give you where I have specifically j plus 1 of them, but that final one is going to be when I have it where it's j plus 2. So the question I have for you is how many 1s are sitting right here? So if I were to count all the 1s before this one, it's going to be j plus 1, but now I'm going to add this extra 2 in. Sorry, not the extra 2, this extra 1 in. All of these in total, this is j plus 2 many of these. Exactly. So now I have actually an exact count of how many 1s there are. And these correspond to the number of times I'm going to perform the recursive case. Does everybody see that? So in fact, it's going to be the total number of 1s, including the base cases operations. This is just going to be what's going to happen at the end. So this is all my recursive stuff that's happening. So this is all the work that happens because of the recursion. This over here is the base case. So now what I want to do, so now I have a lovely equation I can write out that involves j. So that means that, well, it means that t of n is going to be equal to j plus 2 plus 1, right? Because t of 0, this is 1. So like I said, I'm spreading it out like an accordion so I can count how many there are. Now, I have something involving j here. I would like to know something about n. So now watch this. To determine a value for j, we can use, well, I'm going to give this a name. I'll call this equation up here star. We can use star. Because look at this. It has j. It has n in it. So notice n sitting right here. J is over there. I'm just going to do some fun algebra. Notice I can multiply both sides of this by 2 to the power of j plus 2. And notice that this will just dissipate, right? This is just going to go away because there's 0 on the right-hand side. So what do I end up with? I end up with n is equal to 2 to the power 0. Oh yeah, one other detail. Once I do this, I'm going to move all of these 2 to the powers to the right-hand side. Yes, very lovely, very lovely. Somebody's seeing where I'm going with this. So notice all of these 2 to the powers are all going to go to the right-hand side. All of them. So 2 to the power 1, 2 squared, all the way up to 2 to the power of j plus 1. And this is a sum. So now if I write this out as a summation, I would have the sum from I is equal to 0 to j plus 1 of 2 to the power of I. This looks really daunting looking now, but it's actually in a really nice form for us to use. It's actually in a very nice form. Does anybody know what kind of series this is? Anybody? Don't be shy. This has a really well-known name. It starts with a G. Technically, you could go that far. It's a geometric series. It's a geometric series. Yes, it's a geometric series. This is a geometric series. So in particular, it's really nice because it's a finite geometric series. So this is a geometric series. And the lovely thing is we actually have a closed form for this. So this is when, if you were to look at the geometric series, it has a variable called r, usually when the way it's described to you. I'm going to use this. So if I were to apply the geometric series, and particularly the finite version, if I apply to this summation, I'll end up with 2 to the power of 0 minus 2 to the power of j plus 2. It's always one higher. Over 1 minus 2, which if you simplify this down, it's 2 to the power of j plus 2. Sorry, j plus 2 minus 1. So now I have something a little bit easier to play around with. Now I have something in terms of n. So now I have n, and I also have this j here. Now, does anybody have any suggestions what I could do with this now? If I want to figure out what's going on with n. Any suggestions at all? We're right at the end, believe it or not. Yes, we're going to apply a logarithm to both sides and see what happens. So let's head over here. And I must stress that I won't, like if ever on like a test, I won't ask you to give me this closed form. I do actually have this one in the notes. If you look at the optional reading with some background, it has a list of closed forms. That one I used is in there. But I wouldn't ask you to just pull that out of your pocket on a test, just to be very clear. There's only really 2 closed forms I would really expect you to know. It's just the 2 that I've showed you in class. So, anyways, now what I'm going to do is I'm going to move that minus 1 I have to the other side. Move minus 1 to the other side. To the other side, the left-hand side. apply logarithms to both sides. And you'll end up with this. You'll end up with log base 2 of n plus 1. Because moving the minus 1 to the other side means I'm going to add 1 to both sides of the equation. Which this is going to be, because of the equation I have, it's equal to the power of j plus 2. Now here's the great part. There's a lovely property I know about logarithms. Which one could I use here on the right-hand side? There's a lovely thing I could do to this. Yes, exactly. I could drop this power down because of the power rule or power law of logarithms. So I could take j plus 2 right here. And then I'm going to have log base 2 of 2. But what's log base 2 of 2? It's just 1, right? So this is all equal to j plus 2. This is equal to j plus 2. Now, you might say, okay, so what do we do with this now? So, what do we do with all of this? Well, what was j plus 2? That was all those 1s, right? All of those 1s was this, right? That was a little squeaky. Remember that I had the j plus 2. That was all of that. So I can say, therefore, that was a little squeaky. Therefore, t of n is equal to log base 2 of n plus 1 plus 1. Remember, this is from t of 0 over there. And can somebody tell me what this is big O? What's sitting in that big O? Yeah, it's log n. Perfect. And there we go. We got the worst case time complexity for binary search. So one thing I do want to make a quick remark about before we go is that you can actually analyze the space complexity as well of binary search. And you can actually see that the space complexity, depending on how you implement binary search, can differ. So what I'm going to do is I'm going to stop right here. I'm going to ask you to take a quick look at that. It's just a paragraph in the notes. And when we come back, we'll wrap up the last bit of discussion about complexity. Then we're going to start talking about some data structures, and maybe after that we'll be sorting, okay? So that being said, I'll say thank you very much, and have yourself a beautiful day. I'll see you later.